Awesome. We're back. It's 4 o'clock. Time for our 20-minute talks. First up, we have Dre Orfanides with a talk titled Shear Forces, a conceptual model for understanding and coping with risk, change, and technical debt.
Hey, everyone. I'm still Dre. I'm still Associate Head of User Experience at NC State. This talk is about change. And so as Jeff prepared us for in his talk, that means we're going to talk about buildings. All right. So you can think of a building as being composed of a lot of different layers. And let's take a look at the kind of key layers in turn. So every building is located on a site. That gets like location, the plot of land that it's on, the context that it exists in. The exterior of the building has a skin, which is the roof, the siding, all the other weatherproofing, stuff like that. This protects the building as a whole, and in particular, it protects the structure, which is the building's support mechanism, like its skeleton. The services of the building, which are like the plumbing and the electricity and the HVAC and that kind of thing, are like its internal organs, which are supported by the structure. And the space plan, the layout of the doors and rooms and walls and stuff like that, defines the interior of the building. And finally, our stuff inhabits that interior space. Each layer of the building supports and is supported by the adjacent layers. Each layer also has a speed, a rate of change, a rate at which it evolves, changes, breaks down, requires maintenance. So we can ask, how long does it take? How long does each layer last between major changes? So, barring a major geological event, site is essentially eternal. The skin of a building is going to see major renovations every 20 years or so, and a building can go 50 years or even much longer between major structural improvements. Services have a lifetime of like 10 to 20 years before code and technical improvements demand major updates, and the space plan of a building, especially a commercial one, could change every 3 to 5 years or so. Finally, our stuff moves with us every day of our lives. A particular piece of household stuff, like a couch or a TV, could stay in place for years, while another could move several times in the span of a day. These different rates of change create a phenomenon of shear. Each layer has a natural speed at which it changes, but it's either held back or dragged along by the adjacent layers. The concept of shear is borrowed from fluid dynamics, and the application of this concept to buildings was first suggested by architect Frank Duffy and later refined by Stuart Brand in his 1994 book, How Buildings Learn, which I highly recommend. Here's the thing about shear. On the one hand, it can't be avoided because the layers have different speeds by their very nature. On the other hand, too much shear causes turbulence. The movement of one layer will disrupt the activities of the adjacent layers. So let's look at some examples. So there's this construction pattern called slab on grade, and basically you pour the foundation of a building directly on the ground. Now, if you want the bottom floor of your slab on grade building to have plumbing, the typical method is to run the plumbing under the foundation, and then you pour the foundation on top. I think you can see where this is going. Generally speaking, plumbing just doesn't have the same life expectancy as concrete. At some point, you'll likely need to jackhammer through the foundation in order to find and fix a leak or to do some other major plumbing update. This is shear in action. The speed of the surface layer outpaces the structure, and turbulence results in the form of increasing cost to repair the surfaces and unnecessary disruption to the structure. Likewise, space plan has a lot to say about what we do and what we can't do with our stuff. The layout of rooms, doorways, and windows limits where you can put a piano or move a couch or mount a TV. Site is eternal, but we can even have shear between site and structure. The classic example of this is the real estate holdout who refuses to relinquish their property to an eager developer. Although the layers move at different rates, adjacent layers are inextricably linked together. This in itself causes turbulence. At NC State's DHL library, DHL Junior Library, we have an area called the Cone Zone, which was designed as seating for people eating at the adjacent ice cream shop. We're not going to get into that. But despite the tiny cafe tables, it became one of the most popular places for studying. This is partly because the multicolored wall you see is a recent addition, and as such, it has power outlets in it. The seats along the wall have become very popular for laptop users. The wall has just been removed like a week ago as part of a big renovation, and with it, those power outlets are gone. One thing we'll have to think about is how the loss of the power outlet capacity is going to affect the use of the building. Although this provides an example, although services are generally slower moving than the space plan, so to speak, the deployment of services is necessarily tied to the deployment of a space plan. But here's the thing. We can apply the concept of layers to all sorts of systems, not just buildings. While a building has site structure, et cetera, we might think about computing infrastructure similarly. Keeping with the alliterative theme, we can consider the site that is a physical space and infrastructure that supports the server hardware itself, which is provisioned with long and short-term storage. The storage devices are home to operating systems, virtual servers, et cetera, which serve as hosts for the software applications that facilitate our work. And the outcome of that work is stored and maintained in files, our stuff. And just as before, the various layers have different rates at which they see major change. Once again, we're faced with shear. We sometimes see systems pushed well beyond their normal service life due to hardware limitations, leading to potential security issues. For example, many ATMs still run on Windows XP, which reached end of life in 2014. Major updates to key systems lead to upheavals in software as we struggle to update applications in a timely manner. The end of the PHP 5 era left many of us scrambling to update key web apps. Since software tends to evolve faster than we can update storage, we often run up against limitations when trying to run the latest applications. Many of us have come to regret installing an updated version of Photoshop on a computer from the last cycle with limited RAM. With these examples in mind, it's clear that technical debt, the cost that's associated with keeping aging systems on life support, is a manifestation of shear. This idea extends to more than just computers. Every system is made up of components that move at different speeds. As phone technology, cell networks, and mobile OSs evolve, we experience turbulence as we chase the cutting edge or put off upgrading. Investments in media technology become irrelevant as players and media formats and storage paradigms shift. What do you do with your DVDs in an age of Netflix? How many times have you purchased The Princess Bride? The phenomenon of startup disruption is essentially a means of capitalizing on shear. Since regulation always lags innovation, it creates a window of opportunity for disruptors to pursue their goals unfettered. For most of us, though, shear makes organizational management more difficult. What can we do to minimize shear and avoid turbulence? One strategy to attempt to deal with shear is to get out ahead of it by banking on promising up-and-coming technologies. So you might consider this line of LG smart appliances that integrates with Google Assistant to support home automation. Or this wall-mounted dock for your first-generation iPod that connects to your home theater system. Or this high-tech pneumatic tube system, which was intended to send paging requests to the upper floors of DH Hill, and which was abandoned shortly after it was put into service. On second thought, trying to get ahead of the curve might be a bad idea. It's incredibly hard to predict how systems will evolve, and trying to pick one possible future from many is very likely to disappoint. Betting on unproven technologies often proves to be a costly and painful exercise. Another more promising strategy is to simplify the design of layers so that they can be installed and updated more rapidly. Electrical conduit is much easier to install, much easier and faster to install than blind pulling electrical cable through a wall void, and it can be deployed in places where traditional electrical lines can't be run, like on brickwork. Next, thank you. Retrofitting in-floor power is extremely difficult using traditional methods. In response, Steelcase has developed an under-carpet conduit system. And room dividers can allow for relatively rapid reconfiguration of a space plan without the time or expense of a full interior building project. Note that these sped up, simplified layers require compromises. A room divider isn't in practical terms the same as a true wall in terms of privacy, soundproofing, and support for infrastructure. Conduit requires increased material costs and makes aesthetic compromises in exchange for its flexibility, and the Steelcase under carpet system requires proprietary materials and connectors. The most effective strategy towards dealing with shear is to encourage slippage, to design in such a way that adjacent layers have less friction between them, which is maybe contradicting what Jeff said, but that's okay. Since a lot of shear is the result of components aging or wearing out, designing for easy repair and replacement helps to minimize turbulence. Commercial appliances and some household ones are designed in just this way. The motor coupling on a washing machine is a high-wear component, and in some ways it's designed to break in order to protect other components. It's also designed to be easily and cheaply replaced. Similarly, hot swap technology allows for easy repair and replacement of server components with little or no downtime, and this also provides a means to upgrade storage without more extensive changes to the server within limits. The more we can add slippage to the interface between layers, the more we will reduce shear. Access flooring provides easier repairs and even major changes to the services layer with minimal disruption to the space plan. In general, the more modularity we can build into a system, the more we can reduce shear. This goes for both kitchens with standardized components and for modular software design. Improving slippage doesn't come without a cost. Note that in most of these examples, the more flexible systems have a significantly higher upfront cost than their traditional counterparts. More importantly, modular design has to be planned from the outset. It's hard, if not impossible, to retrofit flexibility. Finally, let's think about how we can use this concept of shear as we design and evaluate systems. While shear is inevitable, reducing the overall shear in the system can help us avoid turbulence and disruption. Here are some questions we can ask of a system that will help us see where the shear is and to find opportunities to reduce shear and prevent turbulence. The most fundamental question is, where are the layers? Here too is our first opportunity to reduce shear. Are there layers that can be removed? More layers means more shear surfaces. On the other hand, sometimes it's helpful to add layers. This may seem counterintuitive if we're trying to reduce shear, but an extra layer can sometimes act as a sort of bearing, causing less overall friction. Here's an example from my recent life. So here's a baby carrier. It's meant to be used both as a carrier and as a car seat. It's a lot of work to strap this baby seat into the car, involving wrangling a seat belt and ensuring the seat's positioned right, and this somewhat defeats the purpose of it being both a car seat and a carrier. But of course, this seat comes with a base that's easy to install and provides quick and secure anchoring and removal. In this case, adding a layer makes the whole system less turbulent, even if you have to switch cars or replace the carrier itself. Second, consider the points of contact between the layers. Are there opportunities to improve the slippage between the layers in the event of shear? One perceived failure of Apple's iPhone can be considered a case of poorly designed adjacencies. iPhones have always had non-replaceable batteries, but a high-drain device like a smartphone means a great deal of battery wear. So the battery often wears out before the phone does. This means that when the battery goes, the whole phone does. The layers are too tightly bound and can't slip against each other. Not long ago, Apple revealed that iOS deliberately slowed down the machine as the battery weakened in order to increase battery life. Instead of designing for slippage, they simply traded one sort of turbulence for another. Next, think through the possible futures of the system as it ages. What are the most likely ways a layer will change? How fast do the layers evolve? And which layers are most likely to face upheaval first? Are there opportunities to design the layers to better accommodate those changes? For example, J. Michael Straczynski's sci-fi television series Babylon 5 was meticulously plotted over 5 seasons. However, this presented a sheer risk. The creator couldn't count on every actor to stick through the whole series, so each major character was written with a graceful means of exiting the show to be deployed as needed, with a backup character designated to fill in their roles in case they exited. Changes in one layer will have a ripple effect to adjacent layers. In considering how a layer might change, what are the implications for its neighbors? Can we design or modify layers to better tolerate changes in adjacent layers? In 2003, there was a massive power outage in the northeastern US. The main cause was a system not sufficiently capable of dealing with the after effects of shear. When one part of the grid went out, adjacent grid components couldn't handle the change in load and blew out in turn, in a cascading effect that eventually resulted in 55 million people losing power. Finally, to acknowledge that the world is imperfect, consider what happens if you fail to maintain a layer as the surrounding layers evolve despite it. Can we identify and protect against points of potential failure or accumulations of technical debt? Systems that provide avenues for graceful failure, or at least damage-limiting failure, can help to prevent against neglect as well as unexpected catastrophe. Commercial trucks use air brakes, which are designed so that the air pressure in the system keeps the brakes open until the driver hits the brake pedal. This design works so that if there's a problem with the air system, the brakes actually close. This causes the truck to screech to a halt, but is better than the alternative of the opposite design, which would have the truck hurtling off into oblivion with no brakes if something went wrong. The mental model of shear prompts us to consider the different layers of a system as we plan and evaluate it. If in so doing, if we're better able to identify the key areas of concern with respect to future turbulence and design or redesign the system to minimize that risk. The next time you're considering a system, think in terms of shear to better understand where you might need to plan a change. And that's all I got. Thanks very much. I guess there's like 5 minutes if folks have questions, 4 minutes or something like that. Cool. Thank you. Kate has a question. Is there a mic runner for Kate over here?
That's more of a job. Okay, so if you're going to be thinking about libraries, and let me be fair, library technology, what do you think are some of the layers that are causing the most shear right now?
Oh boy, I probably should have thought of an answer to this question. Putting me on the spot, Kate. I think one thing that we see a lot, well, one thing that I've experienced, here's an example from my own work, is not necessarily library specific, but it does come up in libraries because we're cheapskates. We use a lot of freemium software, and we tend to stick to the free version. We all use Slack to chat in Code4Lib land, and NC State has used like Evernote to do activities in their libraries. And these companies are giving a free product to try to get us to buy a product, but we're librarians, we have no budget, we're not going to buy a product. The way they incentivize people buying their product is by slowly taking away features, and they're often features that we need, and then eventually we look at this product that we were banking our system on, and it's no longer adequate, no longer fit for the use that we were putting it towards. And then we need to reinvent the wheel. That's something that's come up a couple times in my own life, and so that one leaps to mind. It's maybe not the most salient one in the world, but it's bitten me before, so there you go. You might see a similar thing in like major software changes or API changes and suddenly just doesn't support a thing it used to support. If you were counting on that, I think in general in libraries we are counting on functions and features that other people are in charge of developing and maintaining, and we don't have a lot of say with the choices that those people make. So if I was going to paint with a very broad brush, that's kind of where most of the things fall into categorically. How am I on time? Oh, there's a timer. There's 2 minutes left. I didn't see the timer during my whole talk. I was kind of trusting that it was there. Any other questions? I don't see any. I'm just going to assume that there's none. Thank you. Oh, let me fix the damage I've done. That's what I'll do with my last 2 minutes, because I did that thing with the thing. Can we have the other screen up for a second so that I can unbreak my heart? All right. Close this. Come over here. Fix the right click, thank you. Display settings. I've heard rumors that people like it when I go, oh, come on! So there's one just for fun. All right, thanks very much.
Okay, next up we have Clara Turk with the talk entitled Automating Link Management When Institutional Infrastructure Works Against You.
Hi everyone. My name is Clara Turk. I'm a Discovery Systems librarian at McGill University. And I'm here to talk to you about a project I worked on in the last months or so. So I'm going to start by talking about the project, then the problem that I faced, and then different attempts, solution challenges, or when things just kept going wrong. So the project was automating link management. So I think I don't really need to tell everyone that it's getting more and more challenging to maintain access to electronic resources and manage the millions of links that we have in our institutions. And so just for a little bit of context, McGill has millions of electronic resources because it's an e-preferred environment, and I'm sure we're not the only institutions, which just makes the challenge bigger. And we manage our electronic resources through WorldShare, so using OCLC. And until almost now, most of the scripts I wrote for myself. I'm the only one that uses them. They're usually sitting on my own computer, and I ship the results to other people. So I started this project with that state of mind. So the project I was given was to clean up the links in a locally created open access collection in our knowledge base. So that means that instead of just selecting one of the collections that were already in OCLC, we created our own, which means that we have to manage it. And it's a collection that has thousands of links in it, and it's all open access, which means there's not that much information about when the different links update. And so there were thousands of broken links in that collection, and other libraries were using the collection, so we were asked to clean it up at some point, and we weren't really doing it, so I was given the task to do that. So I scripted a solution using Python 3.6, and I used the request library, which is really great if you're working with URLs in Python. And that worked really well until I realized that there were too many broken links to go through them manually and try to find the working link that links to the open access journal, which was our original plan. So I wanted a longer-term management solution to automate a report. So my idea was to get a report that would automatically run once a month and return an email with the broken links so we could maintain it and kind of be ahead. So that way, hopefully, we'd have only a handful of broken links, and we could actually take the time to find the actual working link that links to that. So to do this kind of second part of the project, I used OCLC's knowledge base API, which allowed me to, just with the collection names, just get the kbart, which gives me the list of URLs for every resource in that collection, and then I just loop through that collection and deal with the links accordingly, and then send an email. So all that worked really well, but to fully automate it, I wanted it on university server, because if it's on my computer and I'm on vacation for 3 weeks, well then nothing really happens, or I have to leave my computer open, which I don't want to do. So I thought I'll just put it on university server. And that's when the problem arrived. So it should be a straightforward decision. It's really like long-term management benefits, and then university servers run on Python 2.6. So I went to my requests library that I really like, and there's a note that says that the use of Python 3 is highly preferred over Python 2. Consider upgrading your applications and infrastructure if you find yourself still using Python 2 in production today. If you are using Python 3, congratulations, you are indeed a person of excellent taste. And that also says that the lowest version is Python 2.7. So they're probably talking about Python 2.7. So that was my first problem. I need a new library. Then I also looked at Python 2.6, and end of life was October 29, 2013. End of life for Python 2.7 is declared January 1st, 2020. So even if we upgrade it, I'm still running in the same problem. To be fair, we have Red Hat Enterprise Operating System, which don't support necessarily higher versions of Python. And they do give us security support after end of life, so I don't have to worry about security, but they don't provide support for bugs that have been fixed in later versions of Python. And at least at the McGill libraries, Python community is rather small. Most people script in other languages, so if the demand is not that high to upgrade, then it may be lower on the list for McGill IT to support it themselves. So then I went into different possible solution attempts, challenges, and things just keep going wrong. So to be fair, I'm rather new at this technology world, and I'm still learning a lot, and most of what I knew because I needed to know. So all this world was really new to me. And so in the solutions I'm going to present, some of you might think, what was she thinking? I was trying stuff, and I'm now realizing that I was probably trying stuff that were overly complicated. But you Google things, you ask colleagues, and everyone has different environments and different ideas and backgrounds, so you try stuff. And so I also wanted a sustainable solution, because in the meantime I was offered the systems position, and I figured as a system I was probably going to have more projects on university server than I had as a metadata analyst librarian. So I thought I'd like to not just hack my way through it, but actually find something sustainable. So the first thing I thought about is virtual machines, which I knew nothing about, once again. So I tried Vagrant and VirtualBox. And so it's really neat, because then I think I can separate my two versions, I can separate my libraries, and I can just play around with it and make sure that all dependencies, all requirements work in that little virtual machine without worrying too much, because I did also want to keep my Python 3 version, because I shared it on GitHub, and I shared it with a couple people who I knew were using it, and I didn't want to necessarily force them to go for Python 2.6. And so I tried that, and I could actually never start the Vagrant machine. I kept running. It was running, but then I got blocked at the same place every time, asking me for the private key, and it timed out. And I tried a bunch of solutions. I talked to people who said, oh, but you're on Windows. That's never going to work. Just give it up. And then I Googled Vagrant and Windows, and that didn't really help me that much. I looked at a bunch of things. I tried Hyper-V, which is virtual machine on Windows, but I didn't love that. It was really, internet connection wouldn't go on it. It was overly complicated. And at that point, I kind of got the feeling that there had to be something a bit easier out there that I could do to get this done. And so as I was investigating, I ran into virtual environments. And I thought, oh, that's neat, because it's kind of the same idea of having two environments, and I can manage my libraries and my little world separately, but it's at a smaller scale. I don't have to worry about creating 3 machines. And that also allows me to do it repeatedly very fast, because it's simple. So I started by looking at different Python libraries. And one that caught my attention was pipenv, which is really cool because it combines pip capabilities and virtual environment capabilities, which basically means that you can manage your virtual environments and your libraries all in one neat package. Of course, the lower version you can work with in pipenv is Python 2.7. So then I think, okay, not that one, and all the nifty little GitHub libraries I found all didn't work with Python 2.6, and I tried the Python version ones, but I didn't love it. And so on my laptop I use Anaconda, and in the interface you can create different virtual environments. So I look into that, but that was starting again with Python 2.7. And then I found out that through Anaconda, if you don't use the interface but use just the bash, you can script it in Python 2.6.9. which is not quite as low as McGill's servers, which is Python 2.6.6, but I figured it's probably good enough. And I'll just make sure that the libraries didn't die in between 2.6 and 2.6.9. So I script that, and that went really nicely. I'm translating my script. I found new libraries. It all works really well. I test it. And then I test it with a larger sample. And I got a problem. I got an SSL error that basically meant that 90% of the URLs in the collection weren't actually being searched and weren't being treated by the script. So then it's not really useful. And when I looked into this error a bit more, I found out that that was a bug that was fixed in Python 2.7.6. So this is the point where I got a little discouraged. And I did find one web page that says, if you must use Python 2.6. So I'm going to try that workaround at some point. Also, you know, priorities change, and that I couldn't work on that right now. But I am going to find a solution, and it's going to end up on GitHub. I'm planning on having 2 versions with the libraries working one next to each other. I'm also hoping that maybe as a systems librarian, I have more power to get Python 3 somewhere on the server, but who knows. And I talked way faster than I thought I would. So this is my GitHub. It only has Python 3.6 version on there, since the Python 2.6 isn't working. If this means anything to any one of you, and someone has a really good idea to make this work, please come find me. I have a GitHub and a Twitter and an email, and I am here too. So don't hesitate. Any questions? Thank you.
All right, next up we have Jason Preme with a talk entitled Why Building a Complete Index of Open Access to Research Articles is Hard and How You Can Help.
Can y'all hear me okay? Mic on? Excellent, well done. Our last session of the day, y'all made it, good job. Lucky me, I get this audience at the last session of the day. Looking out here, y'all are nerds. I like it. This is great. Y'all are my people. Seriously, I love this. I don't get to give this many talks in front of nerds so much. So let me tell you my nerdy computer programming joke. All right, knock, knock. Race conditions. Who's there? Anybody? All right, that's good. The rest of y'all will get it later. That's good. I was going to tell a UDP joke, but then I thought maybe you wouldn't get it. All right. And networking people, a couple of y'all. All right. Luckily for you, I'm not going to tell jokes here all day. I actually want to tell a little bit of a story. Y'all seen a lot of presentations today. I thought maybe I won't do a presentation. Instead, I'll just tell a little story. And this story starts, well, I guess like any good story, starts at the beginning. I'm talking the beginning of humanity. Ever since the beginning of humanity, there's been problems. Always with the problems. Someone's dying. Someone's getting sick. Someone's having problems, right? Someone's killing each other. We've got real problems with humanity, right? I didn't say it was going to be a happy story. Right? We got all kinds of problems as humanity. But there is a happy part, and I do think it is a happy story. And the reason for this is because as long as there's been problems, there's been people trying to fix the problems. And when we try and fix problems, typically we do it together. Why is that? Well, because any individual human is very stupid and dies very quickly. Right? That's a problem. On a species level, right? Like we just don't really have the resource. You take Albert Einstein, put him on a planet, right, by himself, what's he come up with? Like, it's not going to be relativity. He'll be lucky if he gets a sharp stick, right? Like, as a group, we have to work together to solve problems, right? As an individual person, like, I'll get read for a second, like, as an individual person, historically, I have a pretty good chance of being born long ago in the past, where I have a pretty good chance of watching my kid die of something that I can't prevent. I got to watch. That's a huge percentage of humans have been in that situation. That's real. I'm not making that up for the point of my story. That's for real. You get smallpox, you got a 30% chance you're not going to make it. And individually, there's nothing I can do about that. I just got to watch. As a species, on the other hand, together, we don't have to be scared of smallpox no more. Smallpox is scared of us. We eliminated that by working together. We work together we can create something. We got to get a lot of brains on a problem before we can fix the problem. We got a lot more problems, so we need a lot more brains, right? So in my story, one of the best years, one of the most exciting years, is 1665. Anybody know what happened in 1665? Anybody? It's a tough one. Plague was happening, that's true. A significant event from my story is in 1665, Oldenburg published the first scientific journal, Philosophical Transactions of the Royal Society. They were not big on punchiness back then. And he created this journal, and it was a good idea. And more journals followed. We got lots of journals today. And the journal is one of the most powerful tools that humanity has ever created for collaborating, for working together, for solving problems together as a group. And that makes it a really good year in my story. An even better year in my story, then, is 2002. Any guesses what might have happened in 2002? That would be relevant for my story. I know a lot of things happened. Any guesses? I can say I got all day. No, I'm just kidding. All right. In 2002, the Budapest Open Access Declaration came out. That's a really exciting moment because it's the beginning of the modern open access movement. Open access movement, right? Saying that instead of just publishing journals and say, well, if you got the money, you can read it or whatever, we'll publish a journal, anybody can read it. So that's a big moment. That's going from 1% of people being able to read it to everybody being able to read it. That's a lot more brains. That's a lot more computing power. That's a lot more working together to solve species-level problems, right? We got species-level problems, then we got to have species-level solutions. Open access is a huge move towards that, and open access has been doing great since then, since 2002. In fact, today, about half of all newly published articles are open access. About half. That's lots. That's millions and millions and millions of articles that anyone can read for free for the first time, literally in human history. We've got half of everything that we've created available to everyone. And that percentage is growing. We're headed for everything, all of our knowledge products being available to all of our people. Right? We got species-level problems. We're closer to having species-level solutions. That's really exciting. So that's the big story. But we only got 20 minutes, so I'm not going to tell that whole big story. I'm going to tell a smaller story. The smaller story doesn't start as far back, thankfully. The smallest story starts in 2017. And me and my co-founder, her name's Heather Pavovar, we have a little nonprofit, and we were building a project. We like to build things. And we were building this project where we thought, hey, we've got an article, and wouldn't it be cool if we could just find out if that article had an open access copy of it somewhere, right? Either on a repository or on the publisher site or just somewhere, right? Where's that article available to read for free? And we couldn't do it. We couldn't do it. There wasn't a single place in the entire world where we could find, given an article, where is it for free? We've got this treasure, maybe the greatest treasure ever created by our species, right? The corpus of all of the scientific articles, and a huge percentage of them free to read for anybody. One of the greatest treasures ever created, and we can't use it. It's like someone gave you, Michelangelo's David in pebble form, right? Like, here's a box full of David. Do you enjoy it? Like, no, it's just a bunch of pebbles, right? We needed to create this. We wanted to find a way to meaningfully access this. We wanted to find a way to defragment the hard drive of humanity's kind of expertise. So we wanted to build this thing. So we built this thing. So we ran into 8 problems along the building of this thing. The thing's called in paywall. Of course, that's what the talk is about. And we ran into 8 problems while creating this thing. I'm going to try and remember all 8. The first problem is, what goes in it? How do we decide what goes in on paywall in this directory of all of the open access? And we thought, well, a good place to start for that was Crossref. I'm guessing people are familiar with Crossref here. Anybody not familiar with Crossref? Anybody? All right. Either a lot of people don't want to raise their hands, or they're all really up on their Crossref. So Crossref has a registry of all the DOIs. The DOI is a unique registry for every scholarly paper. There's about 100 million of them. So we said, OK, great. That'll be kind of our primary key. That'll be kind of where we get started from. So that's what we started with. So we got these 100 million articles. So that was problem 1 solved. So problem 2, we said, OK, well, articles are open access in a lot of different places. A lot of times they're open access on the publisher site. A lot of people call that gold open access. So how do we find gold open access? How do we discover gold open access? And I'm not going to spend a ton of time on that part because I think that's not quite as interesting, and I want to have time for the other half. But I can give you the gist, which is we looked in a bunch of different places. So we looked in the directory of open access journals. We used publisher APIs where those were available. We used the OAI PMH endpoints that many publishers have. We did some automated harvesting, and we did some manual harvesting. We had some people just actually look. And we used the Crossref API. That was another one. The Crossref API has a pretty cool thing about whether something is available hybrid. So using that, we were able to come up with all of the gold open access and all the hybrid open access articles and pull all those into one place. So that part's done. That part wasn't that hard. Then there's a second part, and that's green open access articles. And that means articles that have been archived somewhere by the authors in an open access repository. So how many people here are a manager or otherwise involved in an institutional repository? I'm just curious. OK. Nice. It looks like about maybe 10%, maybe something like that, of the people, which is awesome. Like, institutional repositories are amazing, because call me crazy, but I think it's kind of cool if the authors, the creators of an article, can share it with the world. That's kind of a nice idea, right? That's what they want to do in the first place. I mean, I don't want to get too much into the scholarly publishing model here today, but like something about the idea of taking humanity's greatest treasure, the scholarly record, and saying, hey, I could probably put some fences around this and buy a bigger boat. Something about that just does not sit right with me. So I like the idea of the institutional repository. This repository which allows authors to share their work for free and legally, right? Which is great. There's a couple things that are difficult about institutional repositories, though, which I'll often say is IRs, because as you can tell, I'm stumbling over it. But IRs have this problem where they're underfunded in a lot of institutions. And because of that, the quality of the data that we get is challenging. And there's a challenge in a couple ways. So the first problem we have is actually assembling a list of institutional repositories. So there's a couple lists out there, and that, of course, already suggests the problem, which is there is no one list of institutional repositories. There's a bunch of partial lists that overlap, and there aren't really unique identifiers for the repositories. So we said, well, how do we even assemble where the repositories are? So what we did is we took everybody's lists, put them all together, put them in a big spreadsheet, and then manually went through all of these. And it wasn't that bad. It was about 5,000. It wasn't that great. I mean, I'll go through a spreadsheet of 5,000 URLs, like looking at the websites, trying to figure out, if it's the same as the other website or whatever. But we were able to assemble a list by manually doing that. We also used Mechanical Turk, so we kind of farmed it out, and we're able, for some of the subtasks, we were able to split up in that. So by doing that, we were able to come up with a list of, as far as I know, the most comprehensive list of institutional repositories worldwide. So that was kind of step one. So once we did that, we're like, oh, we're in the clear. We're good to go, right? There's the OAI PMH standard, which is amazing, and it allows us to harvest from the repository. It's really cool. It's an open standard. So by using OAI PMH, we should be able to solve this problem. Done. Alas, it was not that easy. So we pulled all the repository content in, but we found that there was a lot of problems with the metadata. Really big problems with the metadata. In particular, there's a lot of records in an institutional repository that say full text is available, wherein full text ain't available. And I think the reason why they do that is because they're saying that later on full text will be available, which of course isn't really that helpful to me. I'm kind of interested to know whether it is now. And particularly as a user who wants an open access copy of something, the last thing I want is the promise that someday in the eventual future, an open access copy will emerge. I don't want prophecies. I want the actual resource if I can get my hands on it. So we looked at this in a number of ways. There's no way around it. What we ended up having to do is say, well, we just don't trust the metadata. So we created a harvester that actually just goes through every single record from every single institutional repository. It hits the landing page for that record, and then we created a heuristic-based scraper that tries to find out where is the PDF in this page. That's the full text copy that we want. Can we download that? Is it in fact a PDF? And this is one of my favorite parts. Is it a PDF that says PDF coming soon? Because that turns out to also not be what the user wants. So we ended up going through this whole process, and we ultimately ended up solving this. So we have a job now that not only does it pull in the OAI PMH record, but also hits the repository landing page, checks to make sure that's actually what we're looking for, and then we can get a valid PDF down from it. Also, while it's doing that, it automatically tries to detect the version of the PDF, because again, the repository metadata wasn't so trustworthy for that. So it looks for heuristics like, does it say copyright Elsevier on it? Does it say has not yet been peer reviewed? These kinds of things, in order to kind of try and detect the version. So that was that problem done. Next problem. Ideally, in a perfect world, I would love it if every single repository on every single page said, this is the DOI for this particular resource. Right? DOIs are great. I love DOIs, and if they connect to them, that would be great. And some repositories do this. It is unfortunately the exception, not the rule. And so we've got a real problem here, right? So we were able to download about 80 million records from repositories of scholarly content. We got these 80 million records over here. 80 million records, yay, full text, it's great. And then over here, we've got Crossref, 100 million records, things that people are looking for. It has good metadata. It's got like persistent IDs on it. But we didn't have anything between them. When there's a DOI there, great, we can use that, but it's not normally there. We had to find some way to connect these two resources. And so, of course, the only thing we were able to do is use kind of a heuristic-based fingerprint matching, same thing as a human being would, right? So does it have the same title? Obviously, that's not enough. Does it have the same title and the same authors? Well, that's probably pretty good. What if one of the authors has changed? It depends on how many authors there are. It depends on the discipline. What about the year? Well, what if it was in the institutional repository in December of 2017, but it's published in January of 2018, right? So we ended up having to solve all these problems, tuning the algorithm extensively to try and find a way to match one article to another article. My favorite one with this was one where we did the incorrect match. There were two different articles, but they were on the same general topic. They were by the same guy, and they had the exact same title. And I thought, you're running short of ideas, friend. when you're writing the same article, you've got the same title. You should think about maybe like expanding your area. Yeah, so that was that problem solved. So we did this kind of fingerprint matching thing. So that was exciting. Took a lot of work for sure. And it kind of creates, you can probably imagine, the next problem. And the next problem is, what do we do about wrong matches, right? How do we balance precision and recall? And so what we did for this is we created an automated testing framework that uses mechanical Turk. So the Turkers get jobs where they see an article. For the precision task, they see an article. They say, this is the submitted article. Here's the full text that we think we found that matches this article. Is it indeed the same? And based on a human judgment, we can say, yes, it is the same, or no, it isn't. And we can just shovel test articles in there and treat it as just kind of a black box where, yes, this is our precision level at any given time. And so we can run that, and so we can kind of do a little bit more of a test-driven development approach where we're constantly getting new data about our precision. And same thing for recall, right? We test the recall against Google Scholar. We ask real people to search a particular article in Google Scholar, see if what they found, see where are they able to find anything. So, and then we test that against our automated results from on Paywall and see if we were able to find anything and test in that way. I'm happy to report that we compare very nicely with Google Scholar, which I think is pretty cool because Google Scholar, of course, is totally closed access, totally closed code, and whereas what we're doing is open source and open data. So that's that problem solved. The whole thing is working pretty well now at this point, which is nice. But who's going to pay for it? It's not cheap. We're dealing with quite a lot of API traffic. And so we have this kind of more sustainability issue. A lot of people have asked me about that today and yesterday. I've been talking to people about this. And the sustainability plan kind of emerged. We I think kind of got lucky. We had some funding early on to build it, kind of self-funded it really. But then a lot of companies started coming to us and say, hey, we appreciate that this is open data. We can download it, a snapshot. We can use the API, et cetera. But what we really want to do is run a synced copy locally on our own servers. And we're like, well, that would be cool, but it's pretty expensive for us to give you the regular patch files and stuff. Could you, throw in a couple bucks to help offset that cost? And they're like, oh yeah, definitely. We'll give you a bunch of money for that. I'm like, okay. Interesting. So we started talking to people about, hey, could this be a viable sustainability plan for Paywall? And it turned out that it was. And so we were able to reach out to, or they reached out to us really most of the time, to big companies like we've got Elsevier, Clarivate, Digital Science, some big companies that wanted to run these mirrored copies to pay us good money on a yearly subscription to help support the syncing service. And by charging for that part of it, we're able to make everything else free for everybody. You can go to the site right now on paywall.org, download a dump, play with the API. It doesn't require any kind of registration or anything like that. Or you can look at the source code. Part of the way that works is, of course, we're very, very small. So we can do it for much cheaper than Elsevier or something like that. There's only 3 people in the whole organization. And because of that, we don't have to charge a lot of money to stay afloat. And that's appealing to a company like Elsevier or a Clarivate or somebody like that. So let me tell you a little bit about how people are accessing this, because you might want to check it out yourself. I don't know, but it's also kind of cool. One way is, there's a bunch of ways actually, but let me tell you about the top 3. One way is there's a, thank you. One way is there's a web extension. The web extension just sits in your Chrome or your Firefox. When you view a paywalled scholarly article, it hits our API, checks to see if we've got a free version, and if it does, you get a little green tab on the side of your browser. Click the green tab, read the article. Nothing to it, very easy. It's free, it's pretty straightforward for us to build. It has about 200,000 users, and it's growing, which is nice, so hopefully it's getting the data out there. That's one way. Second way is we have integration with link resolvers. SFX is probably the biggest one, but there's a number of other link resolvers. So if you're on campus, you click a link, goes to the link resolver. Oh, bummer, the library doesn't have any holdings. We're going to have to do ILL. Well, before they do that, they call our API. If we do have a copy, we give you an open access copy for the reader instead of what they were going to get before, which was, like I said, nothing. That's been really good. I think it's caught on really well. We've got about 2,000 libraries using that. We get about over 1 million calls per day on that. And we deliver open access at least in the ballpark of a quarter of the time, especially since this is stuff that the library already tried to find and didn't have. So that means we're delivering like 250,000 open access full text every single day to libraries. And I'm really proud of that. It makes me really happy because it's a really cool resource to be able to do totally for free. And it gets to me at this idea of like we got species-wide problems, species-wide solutions. There's one place where you can go and get all this information. And then finally, the third way is people are using it in their institutional repositories to fill out their IRs. So for instance, a lot of times in an IR, you'll have full text from faculty, but faculty don't want to deposit, right? But for every faculty that's authoring it, they've probably got 4 co-authors in some other institution. One of those may have self-archived it. And since we have a central record of all of the open copies, we can find those. So a lot of people have used that to find open copies in other IRs, pull them into their IR to fill it all out, which I think is pretty cool. There's been a lot of small institution repositories. The biggest implementation we have that was Europe PMC, and they were able to go from 4.6 million records to 6 point something. Anyway, they added like 50%. They added 2 million records to Europe PMC just by finding it like stuck in other places online. And I think that's kind of the dream. That's, in my mind, the idea of this defragmenting vision is to be able to say, hey, like, it's one knowledge. There's one species. We've worked on all this together. Wherever it is, let's put it in one place and we can all use it together. This is the culmination of many thousands of years of humans trying to fix problems. Open access is saying, let's really start fixing them together. And hopefully Unpaywall can help provide a little bit of help in that project. So where do you guys fit in? I would love your ideas. We've got this free open database. As I said, we're a lot smarter together than individually. You guys are super creative. You're nerds. You can make things happen, which I love. What are your ideas? What do you want to do? Get in touch with me. I'm easy to find on the internet. I'm not doing anything tonight. Drop me an email. We would love to hear your thoughts. We're going to be launching a number of products this year. I mean, free products, whatever, like tools this year that we'll be using on Paywall. We're going to have a discovery system, so there'll be a little search index for it. We're going to have various analytics tools, so you could kind of look at the open access percentage for your university, things like that. But mostly, I really want to hear your ideas. So please get in touch. We would love to hear from you. And I think that's about it. I don't know if I got time for questions. Yes, sir.
So given some of what's come up before in the conference, can you talk, how do you square the use of mechanical Turk with its implications for undervalued and unrecognized labor practices?
Yeah, great question. We try and pay a fair rate. That's probably where we're coming at it from right now. We look at like what minimum wage is in the US, and we pay that. So we do the tasks ourselves to start off with to figure out how many we can reasonably do in an hour, and then we figure Turkers are going to do about that many per hour, and then we price them at such a rate as that they would make $10 an hour. Any other questions? All right, well, thanks y'all very much.
All day 2 wrap-up. Tonight we've got the game night. Will be held right here in the hotel from 6:30 to 9:30 in the San Jose meeting room. There will be food and drink service from the hotel bar available, but we can't bring in outside food or drink. Please join us for a night of fun. If you brought any games, bring them with you. If you didn't, come and learn something new. Also happening tonight, LibTech Women Meetup is in the 2050 lobby bar. LibTech Women is a supportive space for women and their friends to network, develop skills, build confidence, and lead positive change. They will be meeting from 5:30 to 7:30 in the lobby bar. And finally, there's karaoke offsite at the 7 Bamboo Lounge. Coordinate details in Slack on the channel C4L19-karaoke. But the gist is people will be meeting in the lobby later to share rides over. And there are more details. And there is a sign up, which can be found in the Google Doc at the bit.ly C4L19-karaoke. And the community support volunteers for game night are Justin Coyne and Chad Nelson. They're located in the back of the room and have zebra striped lanyards. The community support volunteer for the evening contact by phone only is Wayne Graham. Use the phone number on the conduct and safety page on the conference website. And if you're giving a talk tomorrow morning, please visit the podium between 8 and 8:45 a.m. to load your presentation onto the computer. And finally, we'd like to thank our bronze sponsors, Atlas Systems, Lyrasis, UCLA Libraries, UC Santa Barbara Library, Penn State University Libraries, SpringShare Penn Libraries, the University of Arizona Libraries, Temple University Libraries, the library at UC San Diego, Oregon State University Libraries and Press, Rutgers School of Communication and Information, University of Houston Libraries, the University of Illinois at Urbana-Champaign School of Information Sciences, and Califa. All right, thanks for coming, guys.